Sometime in the next few years, a person will walk into a hospital with a bacterial infection. The doctors will try one antibiotic, it won't work. They will try another, it won't work either. They will work through every available option, one by one, and each one will fail. The infection will spread, and there will be nothing left to try. This is not a hypothetical scenario from a distant future. It is already happening today. In hospitals in the United States, in Europe, in every developed country on Earth. Patients are dying from infections that would have been trivially treatable 10 years ago because the bacteria causing those infections have evolved to resist every drug we have. The era of antibiotics, the single most transformative development in the history of medicine, the discovery that turned fatal infections into minor inconveniences and made the entire architecture of modern medicine possible, is ending. Not suddenly. Not with a single catastrophic event that the world can point to and respond to, quietly, incrementally, one resistant infection at a time. And the pipeline of new drugs to replace the ones that are failing is, in the assessment of the World Health Organization, almost dry. This is the story of antibiotic resistance. How it works, how we caused it, how far it has already progressed, and what a world without effective antibiotics would actually mean for every person alive today. To understand antibiotic resistance, you first need to understand what antibiotics actually do and why they worked so well for so long. Before antibiotics, bacterial infections were one of the leading causes of death in the developed world. Pneumonia, tuberculosis, sepsis from a wound that became infected, infections following childbirth, scarlet fever. These were not rare conditions confined to the margins of medical practice. They killed millions of people every year across the United States and Europe, including large numbers of otherwise healthy children and adults who had no underlying conditions and no way to fight off a bacterial invasion that the human immune system alone could not reliably defeat. In 1928, a Scottish bacteriologist named Alexander Fleming noticed that a mold had contaminated one of his bacterial cultures and killed the bacteria around it. The mold was penicillium. The compound it produced was penicillin. Fleming understood immediately that he had found something significant, but the full development of penicillin as a medical treatment took over a decade, with Howard Florey and Ernst Chain eventually developing a method to mass produce it in the early 1940s. Penicillin's impact was almost instantaneous and almost impossible to overstate. Soldiers who would previously have died from infected wounds survived. Women who would have died from postpartum infections survived. Children who would have died from scarlet fever or bacterial pneumonia survived. The death toll from bacterial infection in the developed world collapsed within a decade. Conditions that had been effectively death sentences became outpatient treatments. Doctors who had spent their careers watching patients die from infections they were powerless to treat now had a tool that worked. In the decades that followed, the pharmaceutical industry developed dozens of additional antibiotic classes, each targeting bacteria through different mechanisms: penicillins, tetracyclines, macrolides, fluoroquinolones, carbapenems. Each new class expanded the range of infections that could be treated effectively and provided backup options when bacteria developed resistance to earlier drugs. But from the very beginning, the seeds of the current crisis were built into the biology of how bacteria work. Bacteria reproduce at extraordinary speed. A single bacterium can divide every 20 minutes under optimal conditions. This means that in a single day, one bacterium can theoretically produce billions of descendants. Most bacteria reproduce through binary fission, simply splitting into two identical copies of themselves. But bacteria also exchange genetic material horizontally, sharing genes across different strains and even different species through a process called conjugation. They can, in effect, share useful innovations across the bacterial population far faster than any higher organism can adapt. When a population of bacteria is exposed to an antibiotic, the vast majority are killed. But if even one bacterium in the population carries a genetic mutation that allows it to survive exposure to that antibiotic, it will reproduce while all others die. Its descendants will inherit that resistance. And through horizontal gene transfer, the resistance gene can spread to other bacteria in the population rapidly. This is not a flaw in the design of antibiotics. It is simply evolution, doing what evolution does. The problem is not that bacteria can develop resistance. The problem is that human behavior over the past 80 years has massively accelerated the pace at which they do so, while simultaneously creating the conditions that allow resistant strains to spread globally. The two primary drivers of antibiotic resistance are misuse and overuse, and both are occurring on a scale that has fundamentally undermined the effectiveness of drugs that took decades and billions of dollars to develop. Misuse takes several forms. Patients prescribed antibiotics for viral infections such as colds and flu, which antibiotics cannot treat, take them anyway and expose their bacterial populations to unnecessary antibiotic pressure. Patients who are prescribed a course of antibiotics for a genuine bacterial infection stop taking them early when they feel better before the infection is fully cleared, leaving behind the most resistant bacteria in the population rather than eliminating them entirely. Doctors in healthcare systems under time and economic pressure prescribe broad-spectrum antibiotics that kill a wide range of bacteria, including beneficial bacteria in the gut microbiome, rather than narrower drugs targeting only the specific pathogen causing the infection. Overuse is a separate and arguably larger problem. Globally, an estimated 70% of all antibiotics produced are used not in humans, but in livestock agriculture, animals raised for food, particularly in factory farming conditions, where large numbers of animals live in close proximity and infections can spread rapidly, are routinely given antibiotics, both to treat existing infections and, critically, as growth promoters. Low doses of antibiotics given to livestock over extended periods are among the most effective conditions possible for developing resistant bacteria, because the bacteria are continuously exposed to just enough antibiotic pressure to encourage resistance without being eliminated. Resistant bacteria from livestock agriculture do not stay on the farm. They enter the food supply through meat and produce. They enter water supplies through agricultural runoff. They are carried by farm workers and spread into communities. The resistant bacteria circulating in the global human population today have not emerged exclusively from clinical antibiotic use. They have been significantly shaped by decades of agricultural antibiotic use on a global industrial scale. The consequences of these patterns of misuse and overuse have become measurable and stark. In October 2025, the World Health Organization released its most comprehensive global analysis of antibiotic resistance to date. The report, drawing on data from 23 million confirmed bacterial infections across 104 countries, found that 1 in 6 bacterial infections globally is now resistant to the antibiotics used to treat it. In the most severely affected regions, Southeast Asia and the Eastern Mediterranean, the figure is 1 in 3. These are not edge case pathogens in remote locations. These are common bacteria causing urinary tract infections, bloodstream infections, pneumonia, and gastrointestinal illness in patients in hospitals and clinics worldwide. In the United States, the Centers for Disease Control estimates that more than 2.8 million antibiotic-resistant infections occur every year, resulting in at least 35,000 deaths annually. That figure, already alarming, was made significantly worse by the COVID-19 pandemic. The CDC's 2024 report found that 6 categories of resistant hospital infections increased by a combined 20% during the pandemic compared to pre-pandemic levels, driven by increased antibiotic use during COVID-19 treatment and disruptions to infection control protocols. One resistant fungal pathogen, Candida auris, which spreads easily in healthcare facilities and is often resistant to all available antifungal medications, increased nearly fivefold in the United States between 2019 and 2022. Carbapenem-resistant infections caused by bacteria resistant to carbapenems, which are considered one of the last resort classes of antibiotics, surged 69% in the United States in the period studied. One specific type of carbapenem-resistant strain, carrying a gene called NDM, increased by 461%. When scientists model where these trends lead, the projections are serious. A 2024 study published in The Lancet, one of the most comprehensive analyses of AMR mortality ever conducted, estimated that antibiotic resistance will be directly responsible for approximately 1.9 million deaths per year globally by 2050, with an additional 8.2 million deaths associated with AMR. Cumulatively, the study projected that between 2025 and 2050, antimicrobial resistance could kill 39 million people directly and contribute to 169 million deaths overall if current trends continue without significant intervention. These figures are not the ceiling of the potential impact. They are projections based on current trajectories. They assume that existing resistant strains continue to spread at current rates, that the pipeline of new antibiotics remains as limited as it currently is, and that no new antibiotic class is developed to address the most resistant pathogens. They also assume that modern medicine continues to function roughly as it does today. That last assumption is where the deeper implications of antibiotic resistance become genuinely alarming. The treatments and procedures that define modern medicine are not independent of antibiotics. They depend on them completely. Cancer chemotherapy suppresses the immune system, leaving patients vulnerable to infections that a healthy immune system would fight off. Chemotherapy is only viable as a treatment because antibiotic cover can protect immunocompromised patients from those infections. Without effective antibiotics, the risk of fatal infection during chemotherapy becomes dramatically higher, and the calculus of whether chemotherapy is worth pursuing changes fundamentally. Organ transplantation requires long-term immunosuppression to prevent rejection. Transplant patients live with compromised immune systems for years or decades. Their survival depends on the ability to treat infections that their bodies cannot fight on their own. Without effective antibiotics, organ transplantation becomes an unacceptably dangerous procedure. Joint replacements, cardiac surgery, and other major surgical procedures all carry infection risks that are currently managed through antibiotic prophylaxis, antibiotics given before and after surgery to prevent infection at the surgical site. Without effective prophylaxis, the infection risk attached to these procedures rises to levels that would make many of them no longer clinically justifiable. A doctor at Tufts University School of Medicine, speaking on this subject in late 2025, described being unable to offer a cancer patient chemotherapy because of a resistant infection, unable to offer a joint replacement, unable to offer a heart transplant. These are not hypothetical future scenarios. They are documented cases happening now in American hospitals, with current levels of resistance. The standard medical response to the development of resistance in existing drugs has always been to develop new antibiotic classes that work through different mechanisms, staying one step ahead of bacterial evolution. This approach worked reasonably well from the 1940s through the 1980s, as each decade brought new classes of antibiotics that could address resistant strains that had developed against earlier drugs. It stopped working in the 1990s. Since approximately 1990, The number of truly new antibiotic classes reaching clinical use has fallen dramatically. The pharmaceutical industry, facing the economic reality that a successful new antibiotic would be used sparingly and for short courses, generating far less revenue than drugs taken daily for chronic conditions like diabetes or heart disease, largely exited antibiotic research. The economics of antibiotic development are fundamentally broken. You spend billions developing a drug, then doctors are encouraged to use it as little as possible to preserve its effectiveness, and resistant bacteria eventually emerge anyway. From a shareholder perspective, it is simply not an attractive investment. As of 2025, the WHO's review of the antibiotic development pipeline found only 27 antibiotics in clinical development globally that address the bacterial pathogens of most concern. Of those 27, only 6 were classified as genuinely innovative, meaning they work through mechanisms sufficiently different from existing drugs that resistant bacteria would not immediately have existing defenses against them. 27 candidates, 6 truly novel. Against a global bacterial population evolving resistance at a pace that is now measurably outstripping our ability to develop replacements. There are efforts underway to address this. Regulatory changes in several countries have modified approval pathways for antibiotics to make development faster and less expensive. Public funding has been directed toward antibiotic research to compensate for the market failure that drove private investment away. Phage therapy, which uses bacteriophage viruses that naturally prey on specific bacteria, is being explored as an alternative to traditional antibiotics. Researchers are investigating antivirulence approaches that target bacterial ability to cause disease without killing bacteria directly, reducing the evolutionary pressure to develop resistance. Artificial intelligence is being applied to accelerate the identification of new antibiotic compounds. These are meaningful efforts. But the gap between the pace of resistance development and the pace of new drug development has not closed. The WHO's 2025 assessment is clear that existing efforts, while important, are insufficient to reverse the trajectory of global antibiotic resistance without substantially increased investment, coordination, and urgency. The antibiotics that Alexander Fleming discovered by accident in 1928 and that Howard Florey and Ernst Chain turned into one of the most important medicines in history fundamentally transformed what it meant to live in a human body. They made survival from infection the default rather than the exception. They made complex surgery safe. They made cancer treatment viable. They made transplantation possible. They turned the relationship between humanity and bacterial disease from one of helplessness into one of manageable risk. That transformation is not permanent. It was dependent on bacteria remaining susceptible to the drugs used against them, and bacteria, following the same evolutionary logic that has governed life on this planet for billions of years, are no longer cooperating. 1 in 6 bacterial infections globally resists treatment today. The most dangerous resistant strains are increasing by double digits annually. The pipeline of new drugs to replace the ones that are failing is critically thin, and the procedures and treatments that modern medicine is built on, the ones we rely on to survive cancer, replace failing joints, receive donor organs, and come through complex surgery, depend on antibiotics remaining effective. The post-antibiotic era is not a distant threat on a timeline that stretches far enough away to feel abstract. It is a transition that is actively underway, measured not in decades but in the annual statistics of resistant infections and the quiet hospital conversations in which doctors tell patients that the drugs are not working. In 1928, a contaminated Petri dish in a London laboratory changed the relationship between humanity and bacterial disease forever. In 2025, the WHO published data showing that 1 in 6 infections worldwide had found a way to undo that change. The question is not whether antibiotic resistance will reshape modern medicine. It already has. The question is how far that reshaping goes before the world responds with the scale of investment and coordination the problem actually requires. That is antibiotic resistance. If you want to go deeper on the threats and unknown events that are quietly reshaping our world, subscribe to Horizon Archives. We'll see you next time.